Hello and welcome to the last in this short series of videos about noise. This time introducing the subjects of noise factor and noise figure. These are just an alternative and more common way to specify the noise performance of a lot of amplifiers, particularly radio frequency amplifiers and other components. The noise factor is the ratio of the input signal to noise ratio to the output signal to noise ratio, provided the input noise is that due to a single resistor at the system operating temperature, which is usually taken to be about 290 degrees Kelvin. May seem a rather more convoluted definition than the definition of noise temperature, but it's actually a more common way of specifying the noise performance of components. There is a relationship between the noise factor of an amplifier and its noise temperature, which can be worked out as follows. We know that the noise factor, by definition, is the signal to noise ratio at the input, which is the signal input power divided by the noise input power, divided by the signal to noise ratio at the output, which is the signal at the output power divided by the output noise power. And that is SI divided by SO multiplied by NO divided by NI. Right. Well, the input signal power divided by the output signal power, that's just 1 over the power gain. The output noise, well, that is going to be the gain of the amplifier multiplied by the total input noise. So that's the equivalent input noise of the amplifier, NE, plus NI, where NI is the input noise to the system. These two G's cancel, and that ends up with 1 plus the equivalent input noise divided by the input noise. Now the equivalent input noise is just K times the noise temperature of the amplifier times the bandwidth, and the input noise for a noise factor calculation is the temperature of a resistor at the system operating temperature, which I'll just call T, usually taken to be 290 degrees K, as mentioned. So that's just 1 plus TE over T. And that's the simple relationship between the noise factor and the noise temperature. Note that in order to do it, you have to know what the system noise temperature is, but as I've said, usually taken to be 290 degrees K. Last time, we derived a version of the equation for the noise performance of a multiple stage amplifier in terms of its noise temperature. The total equivalent noise temperature was the noise temperature of the first stage plus the noise temperature of the second stage divided by the gain of the first stage plus the noise temperature of the third stage divided by the product of the gains of the first 2 stages, and so on if there are more than 3 stages. We also have this new expression, noise factor, and we know that the noise factor of an amplifier is 1 plus the equivalent noise temperature divided by the system noise temperature. We can substitute in for these noise temperatures here and come up with an expression for the total noise factor of a multiple stage amplifier. First thing we need to do is just manipulate this and get the expression that the equivalent noise temperature is the system noise temperature plus the noise factor minus 1. Therefore, the system temperature divided by the total noise factor of the whole amplifier minus 1, that's just this, must equal the system temperature times the noise factor of the first stage minus 1 plus the system temperature times the noise factor of the second stage minus 1 divided by the gain of the first stage, plus the system temperature times the noise factor of the third stage divided by the product of the first two stages' gains. Just substituting in for the noise temperatures here from this formula here. This term here ends up being T times F minus T, and this term here ends up being, well, actually, first thing to do, divide every term by the system noise temperature to get rid of the T's. Then note that this term here is F minus 1, and that's F1 minus 1 plus F2 minus 1 over G1 plus F3 minus 1 over G1, G2. And then we can get rid of these two minus 1s. They cancel out. We end up with the total noise factor of a multiple stage amplifier is the noise factor of the first stage plus the noise factor of the second stage minus 1 divided by the gain of the first stage plus the noise factor of the third stage minus 1 divided by the product of the gains of the first two stages. And that is Friis's formula for noise factors, named after the Danish engineer Harald Friis. The only topic left to mention then is noise figures. And noise figures are very commonly specified in amplifier datasheets. How is the noise figure related to a noise factor? That's it. The noise figure is just the noise factor expressed in dBs. So you take 10 times the log to the base 10 of the noise factor, and that's the noise figure. That's it. Right. That is the end of this series of short videos about noise. Phew.